My name is Laura Alford. Today I'm going to talk about the effects of loading on your ship. Uh, by loading, I mean not just the original loading that you had where you put your cargo in place and secured it, tied it all down, everything is good. As the ship progresses through its cruise, things are going to change. Your crew will drink up water, you will use up fuel, and you will get tanks that are only partially full with fluid, and you might get ice, all kinds of tricky stuff. This was all going to affect the stability of your ship, and you need to design for this. So these are sort of the tricky loading conditions that I've had in mind. We've done a lot of exploration and operations in the polar regions, and that's only going to increase. So ice on the deck is going to be a significant worry here. Heavy cargo on the deck, offloading heavy cargo from the ship, both of these can affect stability. If you're emptying tanks that are low in the hull, that can be of concern. One of the biggest ones, though, like I mentioned, is this concept of a liquid-free surface, and I'll explain what that means here in this lecture. So, ice on the deck, heavy cargo on the deck. From a stability standpoint, these are the same. All it means is that you have some heavy weights that's up high in the ship. Because it's high, it's going to increase kg, it's increasing the center of gravity, which increases kg. Kg going up means that GM will go down. So you have decreased GM, and GM, if you'll remember, it was our measure of initial stability on the ship. So if you have less GM, then you have less initial stability. Similarly, emptying out weight from the bottom of the ship, if you're emptying out a tank, will cause the center of gravity to rise, which means that the kg will go up, GM will decrease, and you will also have less initial stability. Increased heel can happen when you are offloading or loading cargo. Again, there's no way of getting around this. You have to load cargo onto your ship. However, you need to make sure that you design your ship such that it can handle these conditions. So as I mentioned, one of the big things that I want to cover today is the free surface correction. And what I mean by that is this. You have a tank in this ship, and it has some liquid in it. The tank is not mostly full, it's not mostly empty. So the liquid is free to slosh around. Within the tank, that liquid, the surface of it, has some inertia, and that inertia is going to effectively decrease GM, which means that it's going to effectively make your ship less stable. So here's a little illustration. Go back to this original ship that we've been working with, and we put an empty tank in the bottom. It has these four main points we've been working with. K is the intersection of the keel and the center line, B is the center buoyancy, G is the center of gravity, and M is the metacenter. And recall that the metacenter is that imaginary point that the ship rotates around. Right. We take this ship and we heel it over a little bit. The center buoyancy shifts a little bit. The center of gravity doesn't, because in terms of where it is relative to the ship, nothing's changed. So we draw a line between the new center of buoyancy and M, and we get GZ, which was the righting arm, and GM, which was our measure of initial stability. So now we go back, we take this empty tank, and we put some liquid in the bottom of it. We've added weight, so the draft increases. This has now become a slack tank. A slack just means that it's partially full. All right, the center of gravity has dropped because we added weight down at the bottom of the tank, or bottom of the ship. The center of buoyancy rises because draft has increased. All right. For simplicity's sake, we're going to say that the original metacenter is more or less the same for these cartoons. So if you take that ship and you rotate it, if the liquid was actually a solid, right, which is sort of what we've been working with up to this point, things look the same. You have the center of buoyancy shifts, the center of gravity does not, and you get an initial stability measure with GM. However, because this liquid is not a solid, it slides over, the center of gravity has shifted, right? It moves away from the center line, which gives you not only a new center of gravity, but also gives you a new Z point. This causes, if you draw a line from the new center of gravity up to where it intersects that original center line of the ship, it gives you this new point G double prime. And the distance between the original center of gravity G and this new sort of virtual center of gravity G double prime is what we call the virtual shift of the center of gravity. It's also known as the free surface correction. So now we have this G double prime M. This is the corrected GM. So this is in essence, this is the GM that your ship now has because of this liquid sloshing around in the bottom. And you can see that that's a fairly significant change. GM was rather large, and now we've got, maybe a third of that. So this could be a big deal. One way to get around that is we had one really wide tank in that ship. What happens if we turn it into two tanks, right? You can take that tank and put in a longitudinal bulkhead right there. So now you have two empty tanks. So you took the full beam tank and you split it into two half beam tanks. Again, put some liquid down in the bottom of the tanks. Again, we're going to assume this is the same amount of liquid, so the draft increases the same amount. We have the two slack tanks. G is going to drop again. B rises, more or less the same amount, right? For these examples here, we're going to say that we're going to use this original metacenter again. Going back again, if the liquid was actually a solid, this is what we would get. The center buoyancy would shift over. Center of gravity would not move. Same as before so far, right? Now we let the liquid slosh over, but now look at the difference. Right, because of that longitudinal bulkhead, half that liquid can't slide all the way over to the right. And so the center of gravity still moves, but it doesn't move nearly as much. The result is that the virtual shift in the center of gravity, the free surface correction, is much smaller, resulting in a larger corrected GM. So this is a more stable ship. So that's the importance of longitudinal bulkheads come into play here. Just sort of summarize this then. So for the split tanks, the corrected GM is larger than the corrected GM for the single tank. So in general, this split tank design is going to have greater initial stability than the single tank design. So I kind of like this little slide here. This is obviously, right, the most stable conditions that we're going to have on the ship is when your cargo is fully secured. But that's just not going to happen all the time. Like I mentioned, with the water tanks, as the crew drinks water and takes showers, and as you use up fuel oil, you will have slack tanks. So you have to deal with it. The least stable condition is when you have these really wide tanks. So you want to try and go narrow as you can while still being able to access those tanks and not cause it to be too difficult to unload them, put pumps in, service them, things like that. When you are looking at all of the tanks on your ship, to find the full free surface correction for it is you take up all the individual free surface corrections, those G double primes, for each of the tanks on your ship, and just add them all up. And then you take you take the sum of that, subtract that from your original GMs, the original measure of your initial stability. Original GM minus the total free surface correction for all the tanks in your ship. And that gives you the corrected GM overall for your ship. So you can see that, with this little equation, if you have too many slack tanks, that could cause your corrected GM to be less than 0. So it's definitely something that you should be aware of and you need to design around. One last little concept here before we take off is the concept of list. So whether you have heavy cargo on top of the deck that's loaded off to the side, or you have a very wide tank where liquid is sloshed over, it causes a lateral shift in G. Because of that, it means that GZ is reduced, and you actually get a new equilibrium at some non-zero angle of heel. Right. This non-zero angle is called the angle of list. It affects the GZ curve because it shifts everything down. So the overall magnitude is less because of this off-center line loading. This is something that you will see this when you're loading cargo, right? But this is not a condition that you want to be running at when you're actually transporting cargo. So it's a temporary thing when you're loading cargo. This should not be, if you're designing a ship, though, for operation conditions, you should not have a list because this is not ideal. So those are some things on tricky loading conditions of ships. The next thing to look at is damage stability. So what happens when something happens to compromise the hull of your ship and you need to deal with flooding. So until then, thank you very much.